Well, hello, everyone, and welcome to our February meeting. It's a pleasure to welcome back Steve Bellavia. He has been keeping rather busy as an astrophotographer and amateur astronomer. He has also been Brookhaven's chief mechanical engineer of astronomy's latest eye on the universe, known as the Vera Rubin camera, previously known as the Large Synoptic Survey Telescope, and the LuSEE Night Lunar Radio Telescope. He is going to be discussing their design and what they will be able to do. Give him a big welcome.
Well, you did it right.
Sure. Thank you. Okay, hi everyone, thanks for having me. This is my favorite astronomy club. I just finished telling them I'm going to be a member for life. Okay, so I'm going to talk about two things I've been working on at Brookhaven National Laboratory. The first one being the Vera Rubin Observatory, formerly called Large Synoptic Survey Telescope, or LSST. And then the second half of the presentation is going to be LuSEE Night, which is a radio telescope we are sending to the far side of the moon. And don't say dark side, there's no dark side. So the Vera Rubin, formerly called LSST, that is a picture of where it's kind of at now. It's being constructed. It'll be ready in 2026, we hope. But the observatory itself seems to be built. A little observatory down there called Calypso is also being built. That's going to be used for sending a sodium laser into the sky, not to do live, back up, sorry, can you still hear me that way? Okay, not to do live adaptive optics, but after the fact adaptive optics. It's actually going to correct the photos using the data from Calypso. Okay, so I have a little outline now. We're going to talk about Vera Rubin, the person, not the telescope, what it's named after, and dark matter. We're going to talk a little bit about Edwin Hubble, again, the person, not the telescope, and expansion. Dark energy, gravitational lensing, dark matter, dark energy, and how this ties into Vera Rubin, and supernovae and other science goals of Vera Rubin. So there she is in Lowell Observatory in Flagstaff, Arizona, picture taken in 1965. It looks like they're working on a Colt camera or something down there, I'm not really sure. And it's interesting, so in the late 70s, Vera Rubin and Kent Ford of the Carnegie Institute were confused by these punch card readouts. You know, this is back in the 70s before, computers really were the way they are now. And it seemed like the spiral galaxies were rotating all wrong. The outer edges were moving just as fast as the stuff near the center. And so this was going against Kepler and Newton's laws of motion, of the way we see our planets go around the sun. And this is the beginning of the evidence of dark matter. So I love what she said. In a spiral galaxy, the ratio of dark matter to light matter is about a factor of 10. That's probably a good number for the ratio of our ignorance to knowledge. We're out of kindergarten, but only in about third grade. So she's about right. This is where we are in astronomy. We have evidence of something we know nothing about. So does anybody here know what dark matter is? Like, can they explain what dark matter is? All right, because the good thing is if you don't, nobody knows. These are all the valid theories of dark matter, and some are subsets of others. This is a tongue-in-cheek, humorous Venn diagram of all the theories of dark matter that range from modified general relativity to superstrings to axiom to, the list goes on and on. There's so many, and these are peer-reviewed, well-accepted theories. These aren't the crackpot theories. There's so many theories of what dark matter is. We know what it does, we just don't know what it is. So this is how I like to explain dark matter. Imagine you were a fish that have evolved to be intelligent enough to build a telescope that you could view a flag on land. And you're with your fish scientist, and you say to the other fish scientist, "What's making that flag move?" And the other fish says, "Well, maybe it's air." And the fish says, "What's air?" I can't see anything, right? There's no visible evidence of what's causing that flag to move. Now, we know it's air, because we have a good experience with air and wind and things. But if you're a fish underwater, you don't know what air is. So that's where we're at with dark matter. It's something we can't see and we have no knowledge. We have no knowledge, just like a fish would have no knowledge of air, wind. We have no knowledge of what dark matter is. It's nothing we've ever experienced. And we'll talk about more about the nothing we've ever experienced. How we do it? It's my audio, my. It's not feedback.
Sound off.
Keep going. Let's try that. Testing. 1, 2, 3, testing.
Now working.
Now working well enough to continue. Let's keep going, keep testing. Still muffled. Might be a little too close. Stand back. How about now? Testing.
Eli's.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
That makes sense.
Houston, we have a Elo's landing.
Still got no improvement again.
No
Back to
improvement.
no improvement. Frank
Yeah,
and Eli.
that's not. Is that connected then?
What is that? It's the, that's the hand is coming.
How's that over the phone? Any better? Testing 1, 2, 3. Not great.
Did you share audio when you hit?
Well, they can hear us a little bit. They just can't hear us.
Well.
Well.
They said it's muffled, so. Go canceling speakerphone.
Keep talking into the.
Keep talking into one of those mics.
Continuing to talk. Testing. 1, 2, 3. Testing.
Working on solving technical difficulties.
We're working on fixing this audio issue. For the folks at home. Or around the world.
Okay, so they can hear you.
Okay.
Which one sounds better? This mic or,
Still very muffled.
or Jordan's mic?
Still too muffled to hear on the phone.
They're asking us to increase our volume.
Increase our volume.
Volume, that we can do. Let's do that from.
Hello. Yeah, it's coming.
Echo.
It's coming through.
Maybe you were
That
too
should
close
be.
to the mic.
Maybe I was too close.
Yeah, maybe try standing back.
I'm standing, how about here? Testing. 1, 2, 3. So try this.
Oh,
Good, now I'm getting good.
Now it's getting good. I just have to stand further back. I'll do that.
Getting better.
Use that. You gonna use that one? Let's try this one.
Let's try this one again.
Try this one again. Hello. Testing. Hello. Feedback. Let's use this.
I think last time it worked better when you. Not that close.
This one. Hello. Testing. 1, 2, 3. Is this better? Let's see what the audience says. Back on Zoom land. Is this any better?
The low is good, then it turned back to lots of echo.
This is still echoing now.
Got better now.
Better now, okay, so this is the distance, let's maybe leave these settings. Is this good to continue? Survey says.
Okay, Arthur.
We're okay to go.
Okay, we'll take
Who knows what movies that?
My video froze.
Okay to go.
It's okay to go.
Jack, Jody Foster.
Okay to go. Go ahead.
It was better when you stepped back.
So I sit back here, okay, so let's hold this over there, or I can leave it in the thing, and hold it. But I have no slides, I'm dead. Oh, there we go. Hey. Okay, so is this good? Is this a good spot here? Okay, so I'm gonna hold this over here. All righty. So getting back to my fish analogy, if you were a fish that grew up in the ocean and looked at a flag on Earth, you wouldn't see the air that's making the flag move, and you wouldn't even know what air is. So this is kind of the analogy. So on the left is a galaxy that's what we predicted using Kepler's and Newton's laws for the last couple of hundred years. And on the right is what we observed. This is now confirmed with pretty much every galaxy we look at, including galaxy clusters, that the rotational rates of the stars can't be accounted for by the mass of the stars. And this is why it's called dark matter. It really should be called non-luminous matter. It's basically, if you took the mass of all the stars, it's not even close to adding up to what it should. This is about a factor of 10, which is what Vera Rubin said. It's about a factor of 10 off. There should be 10 times more stars visible because of rotation, and they're not there. So this is why it's called dark matter. So on the left is the graph of our solar system. It doesn't seem like we have any evidence of dark matter in our local area. Mercury moves around the sun really fast, Pluto moves really slow, whether it's a planet or not. And it seems to follow Kepler's laws perfectly. Whereas when you look at the galaxy, not only are the outer portions of the galaxy moving as fast as the center, they might even be moving faster. So this is the data we have for what dark matter is doing. It doesn't tell us what dark matter is, though. And now we're going to talk about expansion. So Edwin Hubble noticed that the farther away something is, the faster it's moving away from us, and that's known as the famous Hubble's law. And it's interesting how he did it. He used Cepheid variables to get the distance to a star, because Cepheid variables, they pulse at a rate proportional to their actual luminosity. So if you know their actual luminosity, and then you know their apparent luminosity, you can easily calculate their distance with the 1/r² law. And then he got their velocity by redshift using spectroscopic data. So a combination of photometric data and spectroscopic data gives you their velocity, so he can make a graph like, so that went up in the graph here, sorry. And parallax is another way to get distance, but you can only get parallax to a certain point. So what we do is we confirm the Cepheid distances with parallax in our galaxy, and then we can use that to get the distance to Cepheids in other galaxies. So that graph here, if you can see, I don't know if you can see the cursor, but the line where parallax stops working is, just about the outskirts of our own galaxy. That's about as good as you can get with parallax, as the angles just become too small. And then we can use Cepheids in other galaxies now to get their distance, and then even supernovae and other things. And then really distance, we can use quasars and type 1a supernovae. So he developed this graph, which is basically that velocity versus distance. And the slope of that graph is the Hubble constant. That's h, right? And it's under debate right now. The Hubble constant isn't 100% verified, and this is because the visual data is disagreeing with the radio data, but it seems to keep getting closer. And it's a big difference from when Hubble just, created this constant. He thought it was 500 kilometers per second per megaparsec. And now the 2021 confirmed number is 70, and that's changing. Now we're in like the high 60s. But what's nice about this is simple, 9th grade algebra. If v equals ho times d, then distance equals v over h, right? It's just if you take the velocity divided by this constant now, which has been verified, now all I need is spectroscopic data, and I've got distance. I only need to know the velocity to get the distance. I don't need to do any other methods of measuring. So now the measuring can be done quickly and more efficiently by just getting redshift. So redshift now is the big thing in astronomy. All you need is redshift. You don't even need Cepheid variables anymore, because the Cepheid variables have verified the Hubble constant, so you just need redshift. So redshift is an important thing. So now we jumped to 2011 from 1929, and Perlmutter, Schmidt, and Rees not only realized that the universe is expanding, but it might be accelerating. It's not just a constant velocity. And this is sort of real data. If you can see, there's not a lot of difference between an accelerating versus decelerating universe, but their data was accurate enough to say that the universe is not just expanding, it's accelerating. So this is a big deal because now we're going to talk about dark energy. So what is dark energy? Well, I teach college physics, and we're always talking about conservation of energy. 1/2 mv squared initial has to equal 1/2 mv squared final, meaning that at best, the velocity of something should remain constant unless you add more energy to it. When a baseball pitcher throws a ball, it can't go any faster than it left his hand unless somebody comes in and scoots it along, right? You can't have something in space moving faster than it was unless you add energy. So now this is what dark energy is. Dark energy is that the universe is not only expanding, it's accelerating, but where is this acceleration coming from? Where is this extra energy coming from that's making a galaxy move faster than it was? It shouldn't, according to our classic physics. So this is another analogy I like. Imagine you grew up on an asteroid and you don't know what gravity is, right? Because you're on very low gravity, and you happen to see a pendulum on Earth swinging, and you're saying, how come it keeps going faster? It's going faster and faster and faster. Well, because of gravity. But if you don't know what gravity is, then you can't explain this phenomenon. So that's where we're at with the universe. We have something that's moving, and it's not because of gravity, it's because of something we have no comprehension of. So this is like the equivalent of the fish and the flag, and now an asteroid being and a pendulum. So I like this pie chart. The pie chart is 4.9% is everything we know, like every atom, every molecule, every chemical reaction, every cheesecake you've ever eaten, every person you've ever known. And the other 95.1% is completely unknown. We don't know what it is. And how can we put these two graphs together, dark energy and dark matter, is because of E equals mc squared. I can always represent matter as energy or energy as matter, as mass. So you can, if you do that, everything according to mass, then this pie chart shows that 95% of the universe is unknown. It's not even fitting any standard classical physics we know. And these are on the right graph. It shows different models. At one point, they thought the universe might be closed, meaning that eventually the gravity would take over and the Big Bang would actually reverse and start collapsing. That's not really a current theory. And then the universe being flat, that was kind of what Einstein was wrestling with. He wasn't sure if, his equations for general relativity were saying that the universe is just going to be the same forever, maybe expanding, but at a constant velocity. And then the next two are open universes that are accelerating. And one of them that's accelerating really fast, where not only does the universe tear itself apart, but atoms tear themselves apart. Even the building blocks of the universe, like the nucleus of an atom is no longer held together. That protons and neutrons no longer bind together. This is a very rapid acceleration, that everything we know expands and sort of, tears itself apart. And what I like is, it seems like people that are in the art and literature people, they're always way ahead of this. I don't know how long ago Robert Frost said this, but he said, some say the world will end in fire and some say in ice. So the closed universe is fire and the open universe is ice. And Robert Frost, kind of predicted current cosmology very well. So now let's get back to Vera Rubin. So I'm reading this from the Vera Rubin, rule book. Is the physics that produces observed accelerating cosmic expansion is a mystery? Is it dark energy arising from quantum fluctuations in the vacuum? Or is this new gravitational physics? In other words, is general relativity not correct? So this is the things Vera Rubin is going to try to solve. It's on its to-do list. So gravitational lensing, I think, and the thing is, all these amateur astronomers know all this. So I feel like you guys are way ahead of me on this. But Sir Arthur Eddington led an expedition to photograph the 1919 total eclipse to see if stars' apparent position moved when they were near the sun, because the sun acts like a gravitational lens because of gravity. And they proved that what Einstein said is true, that the light bends when it passes a high gravitational field. Right? So when you're observing a light the apparent location of the star is not where the star is. It's a starlight got bent so that the star's real location looks like it's somewhere else. And this is what that trip in 1919 did. And then I say, wait a minute, photons don't have any mass. How can they be affected by gravity? How can something with no mass be affected by gravity? And then you got to remember, this is exactly what Galileo said, that the acceleration of an object due to gravity is independent of its mass, no matter how small, even if it's zero, right? So what I like to say is don't try to think about it as something falling on Earth, because you wouldn't think about a photon falling as it's going so fast. Think of it as something with velocity passing something with mass. Basically, mass is a distortion in space-time, so that gravity affects the road that things are traveling. So whether you're a photon or a spaceship or an asteroid, if you're passing a very massive object in the universe, your path is going to be bent. Now, of course, if you're going faster, your path is bent a little less, but it's never zero. This is what Galileo sort of was saying, is that the acceleration number is the same, but if your velocity is higher, it'll have less of an effect. But the acceleration is identical. In fact, Einstein said, gravity isn't like acceleration. It is acceleration. They're equal. Gravity is not a force. Gravity is an acceleration. And this is why this happens. So this is the bending of light. So Vera Rubin is going to use two types of lensing. It's going to use strong lensing. So strong lensing creates, these kind of crazy things where galaxies are so stretched by the masses of galaxies in front of them, in front of our view of them, that they get completely distorted. This is strong gravitational lensing. And that's going to help us with finding where dark matter is and maybe what it is. But more importantly, and this is kind of why Vera Rubin was built, so this is the strong lensing statement, is the weak lensing. Weak lensing is actually a better tool for finding dark matter because dark matter doesn't seem to be in any one place. It seems to be in almost random locations, maybe around the outsides of galaxies. So the weak lensing will help us map where dark matter is. So that doesn't tell us what it is. This is just a baby step towards what it is, right? Where it is. So if we can find out where dark matter is, then we can start maybe trying to figure out what dark matter is. And so the weak lensing was sort of the original goal of the Vera Rubin Telescope. You'll see many, many other goals got thrown on top of it once people realized what it could do. So this is the weak lensing statement. Using redshift is going to probe, the evolution and structure of the cosmic time and ratios of distance versus cosmic time. So it'll set multiple independent strong constraints on the nature of dark matter and dark energy. And then there's other things got going on, counts of clusters of dark matter. We're looking for dark matter clusters using weak gravitational lensing and dark energy. Supernovae are useful because they're standard candles, right? So we can maybe find, further and supernovae that are further out in the galaxy, which are further back in time. That might help us, solve these cosmological questions. And correlations of galaxies, like three-dimensional space epochs that we can figure out what's going on, back in different times, like closer to when galaxies just started to form, what you're getting back to like, billions of years ago. So this is interesting. There's sort of an overlap, right? Cosmology and astronomy. Supernovae are used for both cosmology and astronomy. And then there's an astronomical portion of Vera Rubin. It's not just a cosmology telescope, though that's how it started out. We're going to try to map our own Milky Way and near-Earth objects, so we're going to talk about that. So supernovae, this is nice because I took this picture yesterday. So it fits in perfectly. I had an older one in here, but I figured I might as well make it current. So LSST is going to detect supernovae and do nothing about it except tell other telescopes to go look. It can't stop. Vera Rubin takes a picture for 15 seconds and moves, and another picture, and it moves, and it does the entire sky over 3 nights. So once it discovers a supernova, it has to tell other people, well, I'm done. You guys take over. So the astronomy people with, sort of longer focal length telescopes that can stay on it for weeks or a month or so will study the supernovae. Mainly they're looking for light curves and spectroscopic data and maybe even neutrino detection and things like that. Whereas Vera Rubin is just going to keep moving every 15 seconds. So Vera Rubin will help discover them, but it will move on. So this is part of the astronomy part, is it tells the astronomy people, not the cosmology people, go look at this. There's something going on here you should look at. Mapping. We have mapped from the Gaia satellite and other satellites, but Vera Vera Rubin's gonna probably make it 10 times better. It's gonna get 10 billion stars with enough signal to noise ratio to enable accurate light curves and parallax and proper motion. So, it's hard to map the Milky Way because we're inside it. It's like me asking you to tell me what the shape of your outside of your house is sitting in your living room. It's hard to do. We're inside the same galaxy we're trying to map. But Vera Rubin's gonna help with that. So that's another thing on Vera Rubin's plate. And then near Earth objects. I don't know if people realize this, but in 1998, Congress mandated the discovery of all near Earth objects greater than 1 kilometer in diameter by 2008. I don't know how you know you've got them all, so that's a weird mandate, but then this is Congress. And then 2005, they mandate, they forget 1 kilometer, we want 140 meters, because I think Chelyabinsk was only tens of meters and it caused damage. So 140 meters is still a earth damaging thing. And then you might ask, wait a minute, how does Congress have the right to mandate something? Well, guess who funds all our observatories? So they have the right to do anything they want. So they told us we've got to find them all. So Vera Rubin is we missed the 2020 deadline, but, because we're not running it. But, we're going to get lots and lots of near Earth objects with Vera Rubin because it's just getting everything so quickly. It's getting so much data so quickly. So the bottom line, so we're done with Vera Rubin after this. If you want something, not almost, I didn't talk about the actual building. But if you want something done, give it to a busy telescope. I said it originally started as a dark matter instrument, but became 5 other instruments, all in one because it can do it. So this is my sort of sales pitch for Brookhaven Lab. Brookhaven Lab, the camera was built there, right on Long Island. This is a picture of the full sensor array. It has 9 CCDs per raft. A raft is the thing that's sticking out because it looks kind of like a raft. And there's 21 of these, so there's 189 CCDs. The focal plane is kept at minus 100 degrees C, and the electronic boards are at minus 40. This was a tough feat. This was kind of my job at Brookhaven Lab, was accomplishing that. What's interesting is a single raft. Oops, I guess I don't have that. I got rid of it. A single raft with the 9 CCDs is probably better than any single camera in any observatory on Earth. In fact, they were begging us to make extra rafts. Could you make us one? Make us one? And we couldn't, because we just constrained. But one of those rafts is bigger and better and more sensitive and higher resolution than any camera on any telescope today. And we have 21 of them. So this is pretty cool. So we did some test images. That's, as you can see, that's the shape of the camera. What they do is they take a pinhole photograph of something, even if it's of another photograph. And that's a perfect image. I don't know if you know that. A pinhole camera takes a perfect image. Not perfectly focused. It's soft, but there's no aberrations with a pinhole lens. There's no astigmatisms. There's no pencil. It's just the perfect image. So if you're going to test your camera, you use a pinhole image. So that's a picture of Vera Rubin herself. This is a picture of all the people that worked on the camera in both California, who assembled it, and Long Island that built it. And I'm in it, so I'm very happy with it. So I'm in the test image. So now that's it. So we're done with Vera Rubin. I can take questions now on Vera Rubin, or we can save it to the end.
You just describe the primary mirror, how that has the 3 zones.
I don't even know if I have a picture of that.
And the
I did have that in another talk.
Let
Let me see, do I have any pictures of Vera Rubin? No, I don't. So it's very interesting. What Larry just asked, for those on Zoom, is the Vera Rubin Telescope is called a modified Paul Baker design. It's 3 mirrors. There's a primary mirror. Like a Cassegrain, there's a secondary mirror out in front, but then ground into the center of the primary mirror is a tertiary mirror, which then goes through 3 lenses, and then the camera is behind the 3 lenses. So the camera is facing in, kind of like people that know Hyperstar or RASA telescopes. So the camera faces in, but there's actually 6 optics. Primary mirror, secondary mirror, tertiary mirror, and 3 lenses. And one of the 3 lenses is the largest lens ever built on Earth. It's bigger than the Hale or any of these other giant telescopes. Not Hale, Yerkes, bigger than Yerkes. And the last lens is the vacuum chamber for the camera. So when they designed that lens, they had to take into account how much displacement it would have from pulling it under vacuum. So they had to actually grind the mirror in anticipation of the change in shape. And we're talking like several millimeters worth of change in the middle, not nanometers. So it's very interesting. I said I had another talk, which I actually have on this slide. I can bring it up at the end of the whole optical system. I will do that. So LuSEE night. But before we talk about LuSEE night, I want to just do a little history of radio astronomy. So I just saw recently the movie Holdovers. Does anyone see it? Paul Giamatti makes the best statement in a movie that I've ever heard. I don't know who wrote this line, but it says, "We don't study history to learn about the past. We study history to explain the present." So this is the history of radio astronomy to explain the present of radio astronomy. So as everyone knows, in this room, I know, regular people don't know this, but astronomers know this. 1932, Carl Jansky goes out because there's static on transatlantic phone calls. He's just a regular engineer down in Bell Labs, New Jersey, and he's trying to find the cause of the static. And he detects these Higgs bumps from the center of our galaxy, and there's a little plot of it. And initially, he seems to think it's on a 24-hour cycle, and he writes a paper and says it's the sun. But then he realizes a year later, it's not 24 hours, it's 23 hours and 56 minutes. And everyone in this room knows what that is, though most people don't. That's how fast stars move around the Earth, a little faster because we're not just rotating, but we're moving through space revolving around the sun. And he realizes, him and an astronomer friend realized that the Higgs is from stars, not the sun. So he's listening to the stars. And then everyone knows, him and that astronomer guy. So anyway, it's funny because he runs back to Bell Labs and says, "Oh, I found out what it is. It's the stars. Can we study it?" And they said, "No, get back to work. We can't fix this." And then the next year, him and that astronomer got the Nobel Prize in physics. So, good for him. Bad for Bell Labs. In 1964, everyone knows Penzias and Wilson builds this Horn antenna, and they discover the cosmic microwave background. They discover the remnants of the Big Bang left over from 13.8 billion years ago, and they get a Nobel Prize. And by the way, all Nobel Prizes pretty much go to New Jersey. I don't know if you do that. I think all kinds of things. It's true. The ratio is really weird. Might be the water. I'm not sure. Anyway, and how a radio telescope works. A radio telescope works like a regular telescope. Radio waves, everyone in this room knows that, is light. It's just light you can't see, just like infrared and microwave and all these other forms of light. It hits a mirror, like a telescope mirror, and then it goes to like a sort of a receiver, like a camera or your eye. And then you just have to convert radio signal to whatever you want, whether it's data or a visible image. You can take pictures with radio telescopes, just like you can take a picture with a FLIR camera. That's an infrared. You just have to convert it, those frequencies, back to visible frequencies. It's not that hard. So I like to show this slide is because, the universe is playing in all the frequencies of light, from radio up to gamma rays. But humans can only, at least up until recently, up until maybe 100 years ago, could only detect this skinny little part. It's kind of like going to the Met or Carnegie Hall and missing the whole concert because you can only hear like 6 notes. So this is what the universe is playing, and now we finally are starting to figure out how to hear all of the concert. So imagine if your eyes could see in radio. And now we can. So this is the sky in radio wavelength, right? There's a supernova remnant. There's a star forming region. There's galaxy quasars. The sky is filled with stuff we can't see. Did you have a question? Okay, no, it's okay because I'm happy to answer them. So this is the universe in radio light. So now we can see in radio light. So this is an amazing thing in astronomy. I would say there's in my mind, there's 3 big steps in astronomy: the telescope, Galileo, the spectroscope, and radio telescopes. These 3 things are kind of like the building blocks of everything we know in astronomy. Not that other, X-ray telescopes, gamma ray telescopes, UV are all good, but to me the big ones are radio, spectroscopy, and visual. This is why we know what we know now. So to me, that's the big stuff. And this is the cosmic microwave background, right? This is what initially Penzias and Wilson thought it was uniform. It's only later with Planck's satellite and other data, we realized there's little tiny imperfections or variances, gradients of the cosmic microwave background. And if you do it on a temperature scale, it's down to millikelvin. Like the red regions are 2.7252 Kelvin, and the blue is 2.7248. Right? It's only like 4 millikelvin difference, plus or minus 2 millikelvin, tells you where things formed in the universe and didn't. These are these sort of, wisps of galaxies, like the Virgo cluster and stuff. They actually have the birth pictures of them through this cosmic microwave background. And this is from the WMAP, so this is up to 2012 data. But what people don't know is the stuff that's in orange and yellow. Sometime between Jansky and CMB, Henrik van der Hulst predicts that neutral hydrogen should produce a strong radio signal around FM. It's 1420.4058 megahertz due to the way hydrogen atoms work, the neutral hydrogen atom works. And in 1951, not that much later, Edwin and Purcell detected it. right? So this is the 21 centimeter line, and this is where I'm going with this talk on LuSEE. 21 centimeters is a very, very important line in astronomy, or 1400 megahertz. And I'm not going to go over this slide that very much, but this explains why it happens. It's basically a spin flip of the electron. It's not changing shells like, you know, like normal, like Balmer series in hydrogen. This isn't Balmer series. This is just a spin flip, and the electron creates this 1400 megahertz signal. Kind of think of it like a dipole antenna that keeps alternating its signal, right? This is how the spin flip creates this signal. And it happens naturally in neutral hydrogen. This is a naturally occurring thing. So we built one. We built the 21 centimeter telescope at Brookhaven Lab. This is an area that is in a sump that's now dry, and I run around this at lunchtime. It's a 4-segment with 4-horn stationary. It's a transit telescope. We wait for things to pass. And why would you build this on Long Island? People say this has got to be the worst place on Earth. Talk about light pollution. Radio light pollution on Long Island has got to be like the worst on Earth, maybe worse than Manhattan. Because of airports, we have airports all around with signals and people's cell phones and cell phone towers. That was on purpose. The purpose of this antenna was to figure out what magic we could do in electronics to reduce the noise. So if we can do it on Long Island, we can do it in Chile. So this is called the BMX, the Variant Mapping Experiment. It's an interferometric array that's using 21 centimeter hydrogen, and it has, all kinds of quad ridge ortho transducer, temperature stabilized RF application. We're hitting this with everything we got. Pulse noise injection diodes. We are trying to make this a clean signal out of junk. Anyone that does astrophotography knows this, right? So I don't have this slide, but I like to say this, that the finest French champagne valued at $100,000 a bottle is 85% water. And so is New York City's sewage. Everything's in the 15%. And this is less than the 15%. So this is, anything that matters is in this small little part that we're trying to get out. So this is a picture I took of M81, M82, N, anyone know the third galaxy? NGC 3077. Do you think these galaxies are interacting with each other just based on this visual data? Does it look like they might be interacting? What's any evidence of interaction? Right, we got the little starburst in M82, right? So there's some evidence, right, that these galaxies might be interacting. But what if we could look at this in radio? These galaxies are interacting like crazy. And you wouldn't have known this. If it weren't for radio, you wouldn't have known this. So I like this, my little animated GIF. This is what radio does for you. Radio light lets you see the unseen, right? This is, and this is 21 centimeters. And this is not from Brookhaven Lab. This is from West Virginia, the NRAO. We would probably not be able to do this from Brookhaven Lab. But this shows you the powerful tool that 21 centimeter hydrogen can be. So what's next after BMX? Well, we want to build Puma. Puma will be in Chile, like all good telescopes and radio telescopes are in the desert at altitude. So Puma is an ultra wide band, so it stands for packed ultra wide mapping array. This will be the largest ever built radio telescope array on Earth, not counting radio arrays that are put by telescopes in different places on Earth, like the one that took a picture of the supernova. I mean, of the black hole inside of a supermassive black hole inside of M87 and our own galaxy. But this will be the biggest single array, and we can have up to like a 50% fill factor. They move around, and it'll have 5,000 elements, and it'll be 21. It'll be mostly focused on 21 centimeter, but it'll have 200 to 1100 megahertz range, which I wrote twice for some reason. That's a mistake. And now we get to LuSEE. Sorry, that was just a little introduction, because LuSEE is a little tiny one of these, and there's not much to say about it, so I had to kind of beef it up. So why are we building LuSEE? LuSEE is to study this portion of the formation of the universe. This is another cosmological problem, is the dark ages. This is when the murky soup of gluons and protons and neutrons was so dense that light couldn't make it through. There were no photons. But we do think there might be radio signal. There might be neutral hydrogen that made it out, not visual light. So this is somewhere between reionization and the reionized universe and the initial Big Bang and inflation. And it's very faint and very hard to hear. I like to think of radio as hearing. So that's why we're going to put it on the far side of the moon, where there is zero radio light pollution. So this is a discovery. So LuSEE stands for Lunar Surface Electromagnetic Explorer at Night, LuSEE Night. It's a NASA DOE funded collaboration, and it's really a prototype. They call it a Pathfinder mission. It's a very small radio telescope. It's possible to only run for 14 days, which is lunar night, and then that'll be it. But we're going to do it, and it's possible to run like most things, like the original Mars rover was supposed to run for 90 days, and they ran for 900. So who knows? We might get lucky, but we're not sure it'll survive more than one lunar night because if you don't have solar, which is 14 days, you might not come back alive again. And we're expecting this. We're actually writing several plans for the mission, and one is a 14-night mission, and then there's others that what if it lasts another night and another night. So we have backups. But once again, we're trying to study information from the dark ages. It's going to have a deployable antenna, not very big. It's a really tiny little thing. In fact, all of LuSEE Night would probably fit on this desk. It's not a big thing at all. It's got a lightweight radio receiver and components for power and thermal management, which once again, that was my part of it, as I'm always a thermal guy. And it's a telemetry link to an orbiting satellite. So LuSEE goes up with a satellite that every 14 days you wait and you get the data and send it to Earth. And then it goes around again and you wait another 14 days. And it's going to be launched in 2025. I think that's wrong. I think it's 2026 now. With the commercially provided lander, right? This is the new NASA, sort of picture is commercial. So there it is again. It's once again, it's going to look for highly redshifted 21 centimeter emission, which means it's not really 21 centimeters anymore. It shifts out of the 1420 megahertz range to another frequency, but we know what it is. And B&L designed the core package, right? The radio, the antenna, the unit. We didn't design the lander. So it's what I said. I think I said all this. We did that. And so, how's it going to get there? This is what people like. So, Firefly Aerospace is building the lander. So, this is the equivalent of the LEM, that we did for the Apollo astronauts. They're building the lander that's going to bring it to the moon in 2026, if it goes to plan. And it's going to go on a Falcon 9 rocket. So, a Falcon 9 rocket gets it up there and gets it to the moon, and then Firefly gets us on the moon. So there's a artist rendition of Firefly. It looks an awful lot like the LEM to me. Has everyone been to the Cradle of Aviation and seen the actual? That's a real LEM, by the way. That was the one that was supposed to go on Apollo 16, 17, 19? Apollo 19. So there's a real LEM, not a model at the Cradle of Aviation on Long Island, which is kind of cool. This one called Blue Ghost. I don't know, that's how it got its name. So it's going to land on the moon and hopefully keep LuSEE safe. It's going to make it and be ready to go in 14 days. So this is a really cool picture. This is Earth's polychromatic imaging camera, EPIC. This is a real picture of the far side of the moon with Earth in the background. That's not an artist rendition. That's really cool. And I sketched it not to scale about where LuSEE will be. It's kind of like not far from the moon's equator and not far from its like meridian when it's on the far side, there. So that's where LuSEE will be. I can give you the exact coordinates if you want, but you'll never be able to see it from Earth because it's always on the far side, but not the dark side. A lot of people call it the dark side of the moon, like Pink Floyd. There is no dark side of the moon. It gets eliminated. It just takes, 28 days for the full cycle. So that's where LuSEE will be. It'll be on the far side of the moon. We hope it's at least a 14-day mission because that completes the mission or more. That's the goal. And like I said, it's being built on Long Island again, which is interesting. It seems like a lot of aluminum ends up on the moon from Long Island, right? Like the lunar module built to Grumman. And I think, oh yeah, there's more. So this is neat. This just happened like a week ago. NASA gave us more money to put a second satellite to orbit the moon while LuSEE is there on the same payload. It's going to be on that Falcon 9. So it's going to get the orbiter for the telemetry and this calibration satellite. And this is really cool. So this is a real picture. This is a drone that Justine built herself that has a 1420 megahertz transmitter, and it sweeps over our 21 centimeter telescope to calibrate it, right? And you have to be moving. And this is where I don't know, I'm not really that big in radio astronomy or radio telescopes, but you have to be moving to get a good calibration. So imagine like trying to calibrate your Newtonian, but you have to be moving the laser while you're calibrating. So this is calibrating it, and And with drones, it's tough because the drone has to move like at almost an exact velocity, and then you have to kind of like sweep and let it stop and then come back at some velocity. And like anyone who's ever spray painted a car, like you don't let go of the trigger when you're at the end, you have to go past and let go, otherwise you get a blob of paint, right? Anyway, weird stuff. But anyway, so it's hard to do with the drone, and this is the reason why you want the drone to kind of like, sweep over, and, it increases the uncertainty, decreases the uncertainty from 20% down to about 1%. The calibration really makes a difference for radio telescopes, and it's why you have to do it. So this will help with like understanding polarization. The lunar regolith will actually add noise to the signal because the lunar regolith has like aluminum oxide and stuff in it that's, sort of affects radio signals. So this is going to help that a lot. And what's really cool is this isn't a drone, this is a satellite. Its velocity is perfect. This is like the best calibration tool you could ever have. And it's kind of like just got thrown in like last week, like, oh yeah, we're going to do this too. So now we're kind of scrambling to account for it, to make our electronics and our software deal with this really cool calibration satellite that just got added to the mission. So, and that's the end of the.
How wide will the beam be of this?
Oh, what's the field of view of LuSEE? Good question. It's really big. I'm going to say like 28 degrees or something. It's a really wide field of view because it's a, and they're really just dipole antennas. So it gets a very wide field of view, and we're hoping to record 21 centimeter that happened during the dark ages of universe formation. We're hoping to get signals from here, which is a redshifted 21 centimeter. And I said significantly shifted. When you redshift this far, I forgot what a redshift of 6, I think, is 1 billion years. So this is past redshift 6.
Well, the redshift of the CMB is 1,096.
Right, it's a very big redshift. So that's 13.8 billion years. And I don't know if redshift is linear. I don't think it is.
It deviates.
Yeah.
It gets.
I guess farther. So this is redshift past 6. So that's the ionization, or before and during the ionization. That's the redshift we're looking at. So so redshift of 6, by the way, means that you've moved 6 times the frequency of red. So that's a lot, right? If red is, say, I don't know, 600 nanometers, you've moved 600 times 7 nanometers, 4,200 nanometers in shift. So that's 4,200 nanometers out of the 21 centimeters, which is a lot. That's a big shift in radio world. It's like, you think you were listening to Love 101 and you're listening to Joy 97, You're way off. You're not even on the right station anymore. So, actually, we have a radio telescope at Custer that's tuned into around AM, and we get to hear meteors, which your regular AM in your car will pick up meteors too. But yeah, and lightning and airplane signals and stuff. So this is a little faster than AM. It's in the 1400s megahertz. And my last slide, the very last slide after the end is always, so now it's time for questions. There's always a bunch. Where's, was it, what was his name, Elliot? No. Eli, where's Eli? I wanted to ask him.
You may have to turn the speakers on.
There he is. Hey, Eli.
There he is.
There he is.
Hi, Eli. So we can do, how are we gonna do this? We'll do it by,
We have to turn on.
you get them to hear them. You can get out of the slideshow, actually. Slideshow. You have to get back to Zoom, right? So we can see people. Where'd our Zoom go? There. Here we go. Now, this should be a regular Zoom connection, right? Show purpose.
So you can see a lot.
Hi, somebody. Hi.
Hi, Everett.
Everett, can you say something? Can we hear you?
There's
You should mute it.
Still muted.
Yeah.
There's Eli.
Eli. Can we hear him? Eli, can you say something? There
Something.
you go.
Yeah.
Okay.
All
A question and answer time. Maybe just questions. I might not have answers, just as a warning. Nice guitars.
Yeah.
You have 3 guitars. See, now I don't feel so bad having 15 telescopes. So are there any questions?
Yeah, I was asking, so I saw like some articles on like space.com and other astronomy sources that were saying it's possible that Vera Rubin will discover other planets within the solar system. Do you think that's possible? Or do you
I think
think
that's very possible. Vera Rubin, the magnitude limit of Vera Rubin after stacking for 10 years is 26. Magnitude 26. Pluto is 15. So yeah, I think it's very possible. I mean, I wish it could get to Oort cloud, which is like one of those theories that's never been proven. But certainly Kuiper belt and trans-Neptunian objects will show up on Vera Rubin. And the cool thing is you, Eli, can get that data and you can be the discoverer. Because the data that comes out of Vera Rubin is public. It goes to, I believe, Fermilab first. They kind of wash out military satellites and stuff, and that takes 24 hours. But after that, you get all this data available. If you wanted to follow an asteroid or a comet, because it's doing these pictures every night, you could do that. Or if you wanted to look for something that has not been discovered yet, like look for a dot moving amongst the other dots, kind of like how Pluto was discovered, except now you could do it with software. You could do that. You could discover supernovae in other galaxies. You could do it. I'm saying Vera Rubin could do it. You can do it. The data's there. And it's not hard to use. It's image data. Like you're looking at pictures. I mean, I wouldn't do it visibly. I know the guy we were just talking about this, Larry and I, about Terrence Lovejoy discovers comets with his little, Celestron 8, and he uses software. He's actually having software scan the images and see what dot moved that wasn't moving the day before. Or the week before. So you could do that. You could get software, and probably free, because astronomers always give stuff away for free because they're not very smart that way. They're smart in other ways, but financially they're not. Otherwise, I wouldn't be here. Maybe even, Boca Raton. Anyway, no, I'm just kidding. But no, you can get this data and get software and scan parts of the sky every night and look for a change. This is how supernovae and galaxies are discovered. There's a guy, Tim Puckett, who I heard is retiring, is an amateur astronomer in Georgia. And he's discovered 180 supernovae as an amateur by doing exactly this. He just compares a whole bunch of galaxies night to night with software that looks for a change, looks for a pixel that wasn't there before, a brighter pixel. So yeah, you can do this. And I think Vera Rubin will certainly discover more planets. I don't know if you want to call them planets because Pluto already got in trouble once with this. So, but they'll discover other objects in our solar system for sure. In fact, that's one of the main goals, is to find near-Earth objects. We want to find something that might cross, and by the way, near-Earth object is any object that crosses Earth's orbit, which means that there's a potential to hit Earth, because you just have to have the right timing that, they're crossing Earth's orbit at the same time we're in that spot. So this is a Vera Rubin goal, even without amateurs. But I think amateurs, I think all comets after 2026 will be named, person's name Vera Rubin, because it's going to be the tool to use. It's going to beat out all these other observatories that do, like, ones in Hawaii, you have the one Sloan in Arizona or New Mexico. So yeah, so I think it will. The answer to the question, my long answer is yes. Vera Rubin will definitely discover, you or Vera Rubin, or both combined, will discover other bodies in our solar system. And we have questions in the chat.
How many cameras?
All of them, all 189 sensors work taking exposures every 15 seconds. So every picture is a 3.2 gigapixel picture. So, and that has to be done. This is why those giant circuit boards are in there being cooled to minus 40°C, is we have to get the data out. It ends up being 20 to 30 terabytes of data every night coming out of this camera. So it's 20 to 30 terabytes. That's hard to conceive of. 20 to 30 terabytes comes out of a camera every 8-hour or 12-hour period, because the nights there long and short. But yeah, so it's every single camera runs together, and there's other things that can be done. There's actually different runs. Like there's a normal run of 15-second exposures, but every once in a while they do what they call a deep dive, and they'll run the camera maybe for like minutes or even hours just to get more data in a single part of the sky, and that happens every so often too. And there's 7 filters. The filters range from UV to IR, and not super IR, but IR up to like maybe 2 micron, IR. So we'll have UV maybe like 200 nanometers up to 2,000 nanometers. So a broad range of data. Not as deep IR as say James Webb, but still pretty deep that you can get redshift data like for yourself. Like I said, this is what I said. The cool thing about this is, I didn't go into this because my other Vera Rubin talk that I did here already, I don't want to be redundant, talked about why Vera Rubin. So Tony Tyson, the guy that invented this idea and was on the telescope project from beginning to end, was tired of hearing complaints from astrophysicists how long it takes to get time at an observatory. Like, you want to heck in Hawaii, you better be ready to wait 3 years. You write a proposal with a bunch of other physicists, you got to get really good physicists on your proposal, so the review committee says, oh, all right, here's a group that we might want to give time to. And then you wait 3 years, and then they give you a week on the telescope. And then that week goes by, and you get your data, and now you got to wait another 3 years. But Vera Rubin, this goes away. The images from Vera Rubin are the same or better resolution as Keck, as ESO, as any observatory on Earth. It's the same resolution. That's what people have a hard time understanding. The Vera Rubin telescope, although it's taking much more of the sky, if you zoom in on both the Keck and the Vera Rubin, you get the same data. It's not less data. It's the same amount of data as a full, so it's essentially having 1,000 observatories running at once. That's what it's like. So this is the beauty of Vera Rubin. Vera Rubin is going to be running data continuously, 30 terabytes a night. There's no more waiting. There's no more writing proposals. Go get the data.
There's no spectroscope on it though.
No spectroscope.
So that's different from CAC, which has.
That's true. You can switch in a spectroscope. This is true.
And the other thing is that to get the data from the top of Cerro Pechon, I guess,
Yeah,
La
this is a-
Serena, is that a microwave or how are they gonna do that?
This is a problem. That problem isn't solved yet. There's actually no network link that'll do 30 terabytes a night. So we're not sure yet, but we're hoping by 2026 there is. So that's a problem that isn't really solved yet. There's talk of actually making, believe it or not, tape reels and shipping them.
The guy's gonna drive up from
Sneaker
La
net.
Serena up that road
No, there's
for an
always
hour.
flying it, FedEx flying it. Yeah, they're talking, yeah, the guy drives up the road, takes the tape reels, goes to the airport, FedEx brings it to Fermiland, and maybe, like I said, so it adds a day or two. But you gotta wait a day or two to watch out the military satellites anyway, so maybe you have to wait 3 days total. But no, there's actually talk of that as a backup, but they're hoping by 2026, these sort of microwave links and stuff can handle that kind of throughput. There's talk about uploading to satellites, like multiple satellites, and then bringing that back down.
Because the other two scopes that are on that hill.
Right,
are
ESO and Gemini.
Gemini South and SOAR.
Right.
I think they microwave to La Serena and then they put them on the internet.
Right, I think so. I think that's what Vera Rubin will do too, but it might be multi-microwaves, and it's a lot more data than those scopes. A lot more. It's like I said, it's 30 terabytes a night. It's a lot of data. But it's a lot of data that's free to use, which is amazing, right? And like I said, like imagine like you're a kindergarten teacher and you want to follow an asteroid for the year. Right, every day you can say, where is it? Let's bring up a picture. Oh, look, there it is. Oh, look, it's passing this star. It's going through this constellation. You know, even that has value, you know, just to entice people to get into this hobby or this career. And it goes all the way up to like a student that's going to write his PhD thesis. He doesn't have to now go searching for data. He can get his own data. Imagine writing your own PhD thesis with your own data. You know what I mean? Like to me, this is the future, right? This is, forget, you know, trying to scour it, because don't forget, a lot of data is not public. Like if I'm a scientist working on something, I might not want to share my data, right? You know, so I might have spent a week at Keck and say, no, I'm sorry, that's mine, you know. Whereas with Vera Rubin, it's everyone's, right? There's no proprietary. It's just, you know, I mean, yes, when you discover a comet, the name Vera Rubin has to be in there, but other than that, it's all you owe them is the credit. So, yes, that's a good question. Let's see, were there other questions in the chat? Nice, that was Eli. Okay, so any other questions? I'm open, like I said, this is, I finished really early. I didn't think it was gonna be this fast. Was I talking? Someone had a question there? Yes, no? Okay.
I have a question.
So, actually, I do want to show something. I'm gonna answer your question. You asked about the configuration of the optic. I have that. Ooh, I have it on the flash drive. I don't have it here.
Is there dark matter in the interstellar medium as well as?
Is there dark matter in the interstellar medium, or is it just around galaxies? Nobody knows. This is what those weak lensing data will show. Because the weak lensing data can try to get things away from galaxies to see what distortion there is. Right? If we get weak lensing of galaxies, so this is a really weird thing now. This is where software like rules the world and AI. How do you know if a galaxy was distorted? How do I know what the shape was to begin with? How can I say I'm looking at a galaxy, oh, look at that galaxy, it's distorted. How do I know it's not always been that shape? Well, because Vera Rubin is so sensitive, it's going to survey close galaxies. It'll survey 1 million galaxies that are so close that they didn't have a chance to be distorted. And then it's going to take those shape profiles and say, okay, there's no reason that all galaxies don't have this standard shape. And they project that out into 13.8 billion years, or 67 billion, light years in distance, and say, okay, now we know that these are deviating from the statistical shape of galaxies because we have such good statistics. And this is where it's the math, right? This is where the statistics come in. I'm going to tell you what the normal shape of galaxies are, so I can tell you if they're distorted. So that's a really amazing thing that they can do because of surveying so much. You have so much data that now the statistics becomes relevant. You can tell me what the average shape of a galaxy should be. So now I can tell you if it was distorted coming from a further distance. So that's a really good question. Like I said, so it seems like, based on current data, that the outsides of galaxies have a lot of dark matter. And that's just based on observations of things moving. And it's also interesting, it's an interesting thing that I like. We have about 125 globular clusters orbiting our galaxy. And they seem to be in the dark matter halo. And they were here first. They're twice the age of our galaxy, right? That's a weird thing to think about. That those globular clusters that we're looking at were here before we were here. But yet they're still there. Why? So this is all like tied connected. I think this is all tied together. I think the fact that very old tight formations of these sort of microgalaxies, these 500,000 stars in a globular cluster, are in the dark matter halo. That's got to be some form of evidence that that's where formation began, right? And then the question is, now, so then what happened next, right? Did the matter that was in the interstellar space start gravitating towards the dark matter? And this is what they're looking at, right? This is what they're trying to figure out. So this is really, really, so Galileo discovering that Earth wasn't the center of the universe is going to be nothing compared to when they figure out what dark matter is. I think it's going to be like, oh, that was an easy one. Like, this is going to be a big one. So I want to just get that slide. Hold on, let me get that here. The optics. Got it. We have room in the. So this was the presentation I did for you guys. Maybe this is going back to. This is not LuSEE, so hold on. I wanted to show this is a similar talk, but this one talks about the optics. Well, I'd rather actually not be sharing at this point. Oh, that's not it either. That isn't it either. Oh no, you know what? That might be the wrong one. Here it is. No, this one should have had. Oh, I see this one. You can have the optics. What we're talking to well. No, I don't have it. Okay, so I don't have that optics picture, sorry. Unless I can use the internet.
The picture of the telescope itself, or?
Well, yeah, the optics, actually, hold on, I'm gonna just cheat for a second, we can share this in a second. Cheat. Because there's a bazillion pictures. This is it. I can bring this up and share it. This is actually the Vera Rubin site, I believe. Which is good. I don't want, there we go. I want that. So let's go back and if we can go here and say, share. That. Okay, so I don't want to look at that. So Larry asked about the optics. This is the light path. It's the light comes in from the top here where it says, 2, 3.4, F1. It's a primary mirror, goes to a secondary mirror, comes back to a tertiary, which is ground out of the same blank that the primary is, underneath the football stadium at the University of Arizona, at the Stewart Laboratory, where even European Space Observatory mirrors have been made and others. And then it goes through 3 lenses, and the last lens is the vacuum seal. And this lens is the biggest lens ever built on Earth. So this is the optics. And it's the final is f1.18. That's it's a really fast telescope. It's fast with a really good quality image, which is hard to do. And this is why they picked the modified Paul Baker. It's got 6 elements, but works nicely. So that answers that question about the optics. You can stop sharing again if you want. Okay. So if there's no other questions, I think we're good. All right, so you want to start? Thank you.
All right. Well, thanks everybody for joining. And for those of us who are here, I think we're gonna go to Applebee's.
Yes.
All right. And everybody on the phone, thank you very much for joining us. Bye-bye.
Let's just keep coming.